Hello, and welcome back to another IB Math speedrun with me, Bits. In today's speedrun, we're going to be going through the derivatives of exponential and logarithmic functions and how to apply them. So let's jump right in. So there are four derivatives you need to know for exponential logarithmic functions. First of all, the derivative of e to the x is equal to e to the x. That's number one. The second one is the derivative of a to the x, where a is any constant, is equal to ln a times a to the x. The third one is the derivative of ln x, is equal to 1 over x. And the final one is the derivative of log a to the x, where we have log base a, where a is an integer. I mean, not integer, but real number, is equal to 1 over x ln a. So yeah, we should be able to get all of these. So the question now is, let's jump into some questions to see how we can apply these into real examples. So the first question we're going to go through is, I guess I'll do the odd ones, sure. So we have differentiate the following functions with respect to x. And so the first one is y is equal to 3e to the 5x plus 4. Third one is y is equal to 5 to the 4x. The fifth one is y is equal to e to the cosine x. Fg is y is equal to ln 5x plus 4. So let's solve these questions. So if we need to differentiate the first one, well, we have y is equal to 3e to the 5x plus 4. So, well, we need to use chain rule in order to differentiate this. So we can label u is equal to 5x plus 4. And so therefore y is also equal to 3e to the u. And so through chain rule, we know that the derivative of dy over dx is equal to dy over du times du over dx. So what's dy over du? It's simply 3eu, since we know that the derivative of e to the x is e to the x. So this remains constant. Now we need to multiply it with the derivative of u. 5x plus 4 derivative is 5. So we have 3eu times 5. So we have 15e to the 5x plus 4 as the derivative. Okay, now let's do the next one. Y is equal to 5 to the 4x, and what I mean is y is equal to 5 to the 4x. Well, we need to label u is equal to 4x, and so y is also equal to 5 to the u. So we know dy over dx is equal to dy over du, so let's differentiate 5 to the u, which is going to be ln, I think ln u, 5 to the u. No, it's actually ln 5 times 5 to the u. Oops. So it's ln 5 times 5 to the u times du over dx, which is 4. So we have, this is equal to 4 ln 5 times 5 to the 4x. So this is the answer. Now on to the next one. We need to differentiate e to the cosine x. So we have e to the cosine x. So we have u is equal to cosine x. So we have dy over dx is equal to dy over du, which is e to the u, times du over dx, which is negative sine x. So we have the final answer is negative sine x e to the cosine x. So yep, it's that one. And then finally, we have ln 5x plus 4. So y is equal to ln 5x plus 4. Well, we can label u is equal to 5x plus 4. And so y is equal to ln u. So we know dy over dx will be equal to the derivative of ln u, which is 1 over u, times the derivative of u, which is 5. U with respect to x, which is 5. So we actually have the derivative as 5 over 5x plus 4. Yeah. Okay. On to the next question. And the next question is, we need to use the product rule to find the derivatives of these functions. With respect to x. So the first one is y is equal to 3x e to the 2x plus 4. The third one is y is equal to x cubed ln 2x plus 1. And the fifth one is y is equal to e to the 2x times tan 3x. So let's do the first one, where we have 3x times e to the 2x plus 4. So using product rule, we know this is equal to uv prime plus vu prime. So let's label our u and v. Our u is of course going to be 3x, and our v is going to be e to the 2x plus 4. So the derivative of u is simply 3, and the derivative of v is simply equal to 2 times e to the 2x plus 4. So we have uv prime times vu prime, so this is equal to 3x, times 2, so 6x to the e to the 2x plus 4 plus 3e to the 2x plus 4. So that is the answer for this one. This is dy over dx, just a reminder. Next, we have y is equal to x cubed ln 2x plus 1. So y is equal to x cubed times ln 2x plus 1. So we have u is equal to x cubed, u prime is equal to 3x squared, v is equal to ln 2x plus 1. And then we could chain rule this, but so we get v prime is equal to 2 over 2x plus 1. So now if we product rule this, it's u times v, so we have 2x cubed over 2x plus 1 plus v times u prime. So we have 3x squared ln 2x plus 1. So this is the answer. And then the final question, we have y is e to the 2x times tangent to the 3x. Okay, so if we label u is equal to e to the 2x, then u prime is equal to 2e to the 2x. V is equal to tangent of 3x. And so v prime is equal to 3 secant squared 3x. Since this is chain rule, derivative of tangent is secant squared 3x, then we have to divide 3x, which we get 3. So the final answer we should get is dy over dx is equal to e to the 2x 3 secant squared 3x plus 2e to the 2x times tan 3x. So this is the correct answer. Next, we need to use quotient rule to find the derivatives of these functions. So the first function, actually I'm going to do b since we did e, says y is equal to square root x divided by ln x and d is equal to ln x over 1 plus x. So let's do the first one, where we have y is equal to root x over ln x. I keep on drawing this wrong. ln to n. So, quotient rule, well, we know u is equal to root x. U prime is equal to 1/2 x to the negative 1/2. V is equal to ln x, and v prime is equal to 1 over x. So we need to now differentiate this, and remember quotient rule states that the derivative is equal to v times u prime minus u times v prime all over v squared. So if we replace each part, we have v times u prime. So we have ln x times 1/2 x to the negative 1/2. So we have 1/2 ln x times x to the negative 1/2 minus uv prime, so square root x over x, so minus x to the negative 1/2. Since square root x divided by x will be 1 over square root x, which is x to the negative 1/2, all over v squared. V squared being ln x, so we just have ln x squared. So this should be correct. This is dy over dx. Nice. Okay, and then for the next one, we have ln x over 1 plus x. So we have y is equal to ln x over 1 plus x. So we have u is equal to ln x. U prime is equal to 1 over x. V is equal to 1 plus x. And v prime is equal to 1. So we have v times u prime, so 1 plus x times 1 over x, so we get x to the negative 1 plus 1 minus uv prime, which is ln x times 1, so minus ln x all over v squared, which is 1 plus x squared. So yeah, this should be the correct answer. Next, we have find the derivative of the following function. Y is equal to e to the root x plus 1 over ln x. So, okay, this is already split apart for us. So let's get the derivative of e to the x, square root x first, which we can rewrite as e to the x to the 1/2. So the derivative of this is e to the x to the 1/2 times the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. And now we need to find the derivative of 1 over ln x. I guess we can just do this pretty straightforwardly using quotient rule. So if we have u is equal to 1, u prime is equal to 0, v is equal to ln x, v prime is equal to 1 over x, then we get vu, so 0, minus uv, so minus 1 over x, all over v squared, ln x squared. So we have really negative 1 over x times ln x squared. Yeah, so this should be the answer. Let's just check that. Where are we? Yep, that's correct. Sorry about that. Let's move on to the next one. So we need to find the derivative of this function at this point. So we need to find the derivative of y is equal to square root of 1 plus e to the x at the point 0 square root 2. Okay, so this is fine. Let's get the derivative of this. So this is simply 1 plus e to the x to the 1/2. So we can use chain rule to find out what the derivative is. So this is simply equal to derivative of the inside, e to the x, times the derivative of the outside. So it will be 1/2 e to the x times 1 plus e to the x to the negative 1/2. So this is dy over dx. Now we need to find the gradient at this point. derivative, sorry, at the point. Yeah, so actually not, yeah, just the gradient. So we need to substitute x equals 0. So we have 1/2 times e to the 0, which is 1, times 1 plus e to the 0, which is 2. So we have 1/2 times 2 to the negative 1/2. So that's equal to 1 over 2 root 2. I mean, I think that's it. It's equal to root 2 over 4. There's not much else we can do about it. Yeah. So it's equal to root 2 over 4. Yeah. Next, we need to, okay, so we have a function, f of x is equal to ln x minus x. And so we need to do quite a few things with it. First, show that the function only has one turning point. B, find the coordinates of the turning point and classify its nature. C, state the domain and range of the function. D, write the equation of any asymptotes. E, sketch the curve. Okay, so show the function only has one turning point. We need to get the derivative. So we have f prime of x is equal to 1 over x minus 1. This only has one turning point since this only equals 0 at one point. Find the coordinates of the turning point, classify its nature. So we need to make the gradient 0 is equal to 1 over x minus 1. So surprise, 1 is equal to 1 over x, so the turning point is where x equals 1. Yeah. So this would be coordinates of the turning point. The y value is of course negative 1. Since we plug it in here, ln 1 minus 1 is equal to 0 minus 1, negative 1. We can get the second derivative to find the nature of the turning point. So we get the second derivative is equal to, this is x negative, so negative x and negative 2. So if we put in x equals 1 here, we get negative times 1 to the negative 2, so it's equal to a negative. So this means that the turning point is a maximum. Next, state the domain and range of this original function. The domain is clearly that x is greater than 0 since you can't have ln or any logarithm values less than 0. So we have the domain of the function is equal to x is greater than 0. The range of the function is therefore, what's the least value this can have? The least value is, sorry, I'm back. I'm being so silly. If we know that there's one turning point and that it's a maximum, it means that the range is just any number below that maximum. So negative infinity is less than or equal to f of x is less than or equal to the maximum. I mean, probably not less than or equal to it. Less than f of x, which is less than or equal to the maximum, which is negative 1. Oh, I'm being so silly. Equations of any asymptotes, though. I don't see any as x is tending to infinity, but how about if it tends to the other point in domain, which is x tends to 0? Then this would tend to 0 over 1. So this would actually tend to 0. So this would tend to 0. So x equals 0 should be an asymptote in this graph. Yeah. Because, sorry, I mean, as x tends to 0, this tends to negative infinity. Because we're taking the ln of, ln, as ln tends to 0, then this will tend to negative infinity. So x equals 0 is an asymptote. Finally, sketch the graph. So we have one asymptote at 1, negative 1. I mean, the maximum here, so it has to be a negative function, and we know one asymptote is the y-axis, effectively. Where does it go from here, though? I mean, I kind of assume, I guess it would start curving down like this because of the ln function. So yeah, it would look something like this. So that's that question done. On to the next one. So the next question is, we have f of x is equal to x ln absolute value of x for -2 is less than or equal to x is less than or equal to 2. X is of course not 0. And then 0 for x is equal to 0. So we need to do some things. So first, explain why the function g of x equal to x ln absolute value of x is not defined for x is equal to 0. Find the x intercepts. Show the function has 2 turning points. Identify the nature of the 2 turning points and find their positions. And finally sketch the function. So let's do them one by one. Why is the function g of x is equal to x ln x not defined for x equals 0? Because simply ln x is not defined for x equals 0. Because the natural logarithm function is not defined for x equals 0. It would tend to negative infinity. Next, find the x intercepts. This is where we intercept the x-axis. So we have one x-intercept at x equals 0. I mean, x-intercept is when y equals 0. So this is when x equals 0. And then we need to find zeros of x ln x, more or less. So absolute value of x, and so the only other values this would occur for is when ln absolute value of x is equal to 0. So therefore, absolute value of x is equal to 1. So x is equal to plus or minus 1. So those should be the zeros. So 0 and plus or minus 1. Yeah. Next. Show the function has 2 turning points. Let's get the derivative of x ln absolute value of x. So this is a piecewise function. This is x ln x for x is greater than 0. I mean, and less than 2. So 0 is greater, x is greater than 2. We have 0 for x is equal to 0. And we have x ln negative x for -2 is less than or x is less than or 0. So if we get the derivative of each part, we get dx is equal to, this is ln x plus 1 for 0 is less than or x is less than or 2. Since we use product rule, derivative of x is 1, so ln x. Derivative of ln x is 1 over x. 1 over x times x is 1. Derivative is still 0 for x equals 0, but we're not going to find anything there. And then for this lower one, x ln minus x, we get ln minus x plus derivative of this is -1 over x. So ln minus x minus 1. Sorry. For -2 is less than x is less than 0. So we need to find turning points. So this is when dy over dx is 0. So we have 2. This is when 0 is equal to ln x plus 1. Of course, 0 will not be a turning point. And the other one is 0 is equal to ln of negative x minus 1. So these will be our 2 turning points, and indeed we have 2. Identify the nature and find the exact positions. Well, let's find the exact positions first. So we have -1 is equal to ln x So x must be equal to, well, e to the negative 1. Essentially is what we're saying. And for this case, we have 1 is equal to ln of minus x. So x must be equal to negative e. Yeah. Wait, negative e. Oh wait, no, sorry, I made a mistake. This should be. This is of course. Wait, I just can't subtract minus 1. So x is equal to minus e to the minus 1. So there's 2 turning points. To find their nature, we can get the derivatives of these again. So this is equal to 1 over x. So 1 over e to the negative 1 is e. So this is a minimum. And then next for this other one, we have negative 1 over x. Wait, we have 2 minimums, I think. Is this correct? No. No, that's not correct. Derivative should be negative 1. Negative 1 over, negative 1 over negative 1, which is just 1 over x. So, in this case, this would be a maximum. So that's that, and then what else do we need to find? Find their positions, actually. We need to substitute. So x, we need to substitute them back in. So we need to substitute e to the negative 1 and negative e to the negative 1. So this is e to the negative 1 ln e to the negative 1. So this is negative e to the negative 1 for this, and it's e to the negative 1 for the other one. So this would be e to the negative 1, negative e to the negative 1, and negative e to the negative 1, and e to the negative 1. So the function, should look something like this, where we have a maximum here, positive y value with negative x value, and negative x value with positive y value. Okay, on to the final question. And the final question is, f of x is equal to e to the x sine x for negative 3 over 2 pi is less than x is less than 3 over 2 pi. So first, show that f of x has 2 turning points and 2 points of inflection. Next, identify the nature of the turning points and the value of the x coordinate at each one. At the e coordinate. Next, find the coordinates of the points of inflection and sketch the graph. And finally, show that the normal at one point of inflection is parallel to the tangent at the other. E to the x sine x. Okay, so 2 turning points, 2 points of inflection. Let's get the derivative. F prime is equal to e to the x sine x plus e to the x cosine x. And then f double prime x is equal to, I'm sure there's a way to simplify this actually, but this would be e to the x sine x plus e to the x plus 2e to the x cosine x minus e to the x sine x. So these two at the end would cancel out, so it's just 2e to the x times cosine x. So let's get the number of turning points, which is when this is 0. So 0 is equal to e to the x sine x plus e to the x cosine x. E to the x will never reach 0, so we can factor that out. So this will be equal to sine x plus is equal to negative cosine x. And in other words, tangent of x is equal to -1, for which there are two values between 3/2 pi negative. Are there two values? The two values should be actually 3/2 pi and negative 3/2 pi themselves. Yeah. No, sorry, no. This would be negative pi over 4 and 3 pi over 4, not 3/2. Yeah. Next, two inflection points. 0 is equal to 2e to the x cosine x. So it's equal to cosine x is equal to 0, for which there are, of course, 2 points. These would be 0 and pi over. Sorry, no, it would be pi and negative pi, since 0 may not be an inflection point. So let's find the coordinates of the points of inflection. So we already have the x coordinates. So we have pi over 4 something, negative pi over 4 something, and then 3 pi over 4 something. So if we put them into the original equation, which is e to the x sine x, this will be equal to sine negative pi over 4, so that's negative root 2 over 2, e to the pi over 4. And then this would be actually positive. This would be 2 over root 2, e to the 3 pi over 4. And whether we need to find which one's a minimum and which one's a maximum. So if we put it into the second equation, 2e to the x cosine x, negative pi over 4 will be, well, e will always be greater than 0, so we're actually looking at cosine x. Cosine negative pi over 4 is actually positive, and cosine 3 pi over 4 is negative. So this is a minimum, and this is a maximum. Yeah, coordinates of the points of inflection. So in this case, coordinates of the points of inflection are pi over 2 and negative pi over 2. And what's the other coordinate? We need to e to x sine x. So we have, this is 1, so this is e to the pi over 2. And this other one is -1 to the pi over 2. And then sketch the graph, I guess. So pi over 2, negative pi over 4. So this is a minimum. So this would look like this. Drop down the minimum. So this point of inflection is at pi over 2 e to the pi over 2. And the minimum is below the x-axis. And then we have our next point of inflection at negative pi over 2. Oh, wait. No, I missed one. No, I didn't. Yeah, so this should be okay. So then it should sort of curve up like that again. Have a point of inflection before the maximum point on this curve. And then it's concave down. So, yeah, it should look... Hold on. No, this is skewed vastly. I made a mistake. Sorry about that. So, oh wait, the minimum comes first actually too. So it should look like this, and then we have a concave down, and then a much bigger concave up, and then a much larger concave down. So it would like spiral out of control in a sense. It's the x-axis, and then I think we have a point at 0. I think this crosses 0. Yeah, because sine x equals 0. So the graph would look something like this. And then the final question is, show the normal at one point of inflection is parallel to the tangent at the other. So we need to plug in these pi over 2's into this equation. So we have e to the x sine x plus e to the x cosine x. So we have, for this one, this is equal to e to the pi over 2 sine pi over 2, which is 1 times what's it called, plus e to the pi over 2 cosine pi over 2, which is 0. So the tangent line is equal to e to the pi over 2. So normal would be at this point equal to e to the negative e to the negative pi over 2. And then for this line over here, we have negative pi over 2. So ex sine x would be equal to negative e to the negative pi over 2. So this is the tangent and this is the normal. So you can see that the normal is equal to the tangent. So they would be parallel because the gradients are equal. So yeah, that was all for the speedrun. I hope you enjoyed it and I hope to see you in the next one. See you then.